Hello everyone, in today's video we are going to solve a very tricky algebra problem. The problem is in front of us. A polynomial is given whose coefficients are all integers, okay, and four numbers are given: 2 by 3, 3 by 4, 4 by 5 and 5 by 6. The question is which one is the root, okay, of this polynomial. Okay, the coefficients here are large numbers: 60, 97, 71 and so on, and therefore if you want to plug these values in here, instead of x, if you put 2 by 3 and then do calculation, it is a tedious job, right? So is for 3 by 4, 4 by 5 and 5 by 6. So you cannot manually check which one is the root, given that one of these, exactly one of these is a root of this, okay, root of this polynomial. So even given that, it is very hard to find out which one is the root of this polynomial. Of course, there are some tricks, and in this video we are going to use a trick to solve this problem. And once you know this particular trick, you will just need a second to find out which one is the root of this given polynomial. Okay, without further ado, let us dive into it. Okay, so we will solve this problem in a general setting. Okay, one polynomial is given. This is cn x to the n plus cn minus x to the n minus 1 plus dot dot plus cn x plus cn c0. Okay, so this is a general polynomial, and in this setting we will develop the theory and then we will apply that theory to our particular problem. Okay, so one of the important assumptions here is that all these numbers or coefficients here are integers. So basically ci are all integers, which means we can say that this polynomial is with integer coefficients. Okay, that's all. Now suppose it has a root, okay, of the form a by b. So basically we are assuming that, okay, this polynomial is integral polynomial, which means all integer coefficients, and it has a root or rational root of the form a by b. So then a and b are integers. We also assume that a by b is in the most reduced form, which means what? GCD of AB is 1. I mean, this is without actually loss of generality. We can always assume that, because at some point we will get this to be GCD to be 1. Okay, fine. So we are assuming that a by b is a root of this polynomial, and we will develop theory. We will see what happens when a by b is a root of a polynomial with integer coefficient. That's all what we are going to find out. Okay, fine. So if a by b is a root, then in place of x, if I write a by b, the p of a by b after calculation, this should give 0. That is the meaning of a by b being a root of this polynomial, right? Okay, so if p a by b is 0, then what happens? Just put x equal to a by b here, and in the expression as well, right? So instead of x, we are putting a by b, and to the power n, to the power n minus 1 and so on. So we simply put x equal to a by b. Okay, so then what is the value of this expression? Cn a by b to the power n and so on. It is just 0, simply because p a by b is 0, right? A by b being a root of this polynomial. Fine. This is so super easy actually. Well, so from here, let us record this here in the next slide. So cn a by b to the power n, cn minus 1 a by b to the power n minus 1 and so on is actually 0. Now from here, if we just remove the round brackets, what it becomes is this: cn a to the power n by b to the power n plus cn minus 1 a to the power n minus 1 by b to the power n minus 1 and so on, as it was, just removing this parenthesis. Fine. So now we multiply this equation, both the sides, right and left, by b to the power n. So if we multiply this equation by b to the n on both the sides, what we get is simply this. So cn a to the power n, b to the n is gone, and then it was b to the n minus 1, so it remains only b here, and then here it was b in the denominator, so c1a b to the n minus 1 plus c0 b to the power n, and on the right, 0 times b to the n is simply 0. Fine. So here all these are numbers, right? Cn, basically cn minus 1, c1 and c0, these are coefficients, therefore we have assumed that they are integers, right? And a and b, they are also integers, right? Because the root is of the form, or the rational root is of the form a by b, where a and b are integers. So all of them are integers. Now this is kind of a master equation, and all the results will follow from this equation. How? We'll see in a few minutes. Okay, so from this expression, what we can write is this. So cn a to the n is as it was here on the left, and then we move all these to the right. Fine. So they come with this negative sign. Okay, fine. All the plus signs are now negative signs here. Okay. Now, one obvious observations, you can see that cn minus 1 a to the n minus 1 b, product of this is an integer, and this integer is divisible by b because b is already sitting there, right? Similarly, for all the intermediate terms here and here b to the n minus 1, therefore this whole number c1 a b to the n is also divisible by 1, and so is c0 b to the n. So basically on the right, all the numbers are divisible by b. Okay, which means what? The number b divides RHS, right hand side here. Okay, fine. And therefore, since b divides RHS, b also divides LHS, and on LHS we have only cn a to the n. So what we get is this: b divides cn a to the power n. Fine. Now, do you remember this fact that GCD of BA is 1? Actually, GCD of AB1 is equivalent to GCD of BA1. Fine. So, GCD of BA1 means GCD of BA to the power n is also 1. Okay. And once GCD of BA to the power n is 1, what do we get? This is extremely important, and this is very basic mathematics also. So, B divides product of two numbers, Cn and a to the power n, right? Now, b divides the product of these two, but GCD of b and the second factor is 1, as we see here. Therefore, b must divide cn itself. Okay. So, this implies b divides cn itself. This is very simple check and very easy mathematics. One can manually check, no problem, with some examples. Fine. So, what we get is this: if a by b is a root, then b divides cn. Okay, fine. And again, from this master equation we will deduce something else. So again, I have recorded the master equation here, and from there we can write this: cn a to the n, and so on. All these terms, just we have moved c0 b to the n to the right, and therefore it comes with a negative sign. Fine. So now on the left you see that a to the n is there, a to the n minus 1 is there. All the intermediate terms here has a inside that, and c1 a b to the n minus 1 also has a. Therefore, all these numbers, all these terms, okay, are divisible by a, the number a, right? And therefore, what we can see here, that a divides whole of LHS, because a individually divides all of them. Therefore, a divides some of them. That's all. Simple, pretty simple. So a divides LHS, right? And therefore, a must divide RHS, okay? And that implies a divides c0 b to the n, because negative or positive, it does not matter as long as we are talking about divisibility, right? So a divides c0 b to the n. Now again, same logic. GCD of AB is 1, okay, that is the assumption. We can always find such a, no problem. And then GCD of a b to the n is therefore 1, fine. And they imply this: a divides c0. Why? Because a divides product of c0 and b to the n, and GCD of a and b to the n is 1 from here. Therefore, a in particular divides this individual number c0, which is here. So we'll summarize now what we have done. So suppose we have a general polynomial cnx to the n plus cn minus 1x to the n minus 1 plus dot dot plus c1x plus c0 with ci all integers. Then if a by b is a root with GCD of AB equal to 1. So basically, if there is a number a by b, rational number, which is a root of this polynomial, and it is in the lowest term, which means GCD of AB is 1, then a divides c0, which means the numerator of the root, rational root, divides the constant term. Numerator is a, so a divides c0 means numerator divides the constant term of the polynomial, and the denominator is b, b divides cn. So b means denominator divides the leading coefficient. Leading coefficient means the coefficient of the highest degree term. Okay, these two things we have proved: a divides c0, which is here, and in the previous slide we have proved that b divides cn. Okay, that's all. We are ready to answer the question in a second. Okay, let us go back to the first slide. So this polynomial is given. Just check whether this is a polynomial with integer coefficients. Of course, yes, 60, 97, 71, 43, 14. All are integers. Fine. Now, all the options here, you can see that GCD is 1 because GCD of 2 and 3 is 1. GCD of 3 and 4 is 1. So is for this 4 and 5 and 5 and 6. They are just consecutive integers. Therefore, GCD of them is always 1. No problem in that. So all of them are satisfying GCD of AB equal to 1. Fine. Now, you see that denominator, what we have proved, the denominator must divide the leading term. 3 divides 60, 4 divides 60, 5 divides 60, 6 also divides the leading coefficient 60, right? Because x to the power 4 is the highest degree here, right? So 60 is the leading term. Fine. So all these denominators actually divide 60. So we are still not sure which one will be the root. But now if you come to the second thing, that numerator divides the constant term, it is sorted out, right? 5 does not divide 14, 4 does not divide 14, 3 does not divide 14, but 2 does divide 14. So for 2 by 3, both are actually satisfied. So denominator is dividing the leading coefficient and 2, which is the numerator, dividing the constant term. So since only one of these is the exact root, we have the answer 2 over 3, and that is the root of this polynomial. Okay, this is the trick, and once we know the trick, we see that it takes just a second to answer the question. And this is an extremely important trick which is useful, very, very useful in competitive exams. Therefore we have presented already a full video on this trick. Okay, yeah, that's all in this video. If you found this content interesting, do press the like button and subscribe our channel to motivate us. I sincerely thank you for watching this video.